Welcome to this video on partial fractions decomposition. Here we look at a different kind of problem than you've seen in the type 1, 2, or 3 videos if you've been watching those. What we're going to do is we're going to decompose this fraction into the sum of multiple fractions, as we always do in partial fractions decomposition. Now, the first thing you would always do, of course, is factor your denominator. This denominator factors into x minus 2 times x minus 2, also known as x minus 2 quantity squared. Now, you might recognize this as a type 2 problem. Sorry, type 3 problem if you've been watching all my videos up until this point. But either which way, what I'm going to do here is take you down a path where I show you a procedure that you've seen before, but it's going to lead to some kind of a contradiction based on a false assumption. This first part of this video is essentially going to show you the wrong way to do this problem, but I think it'll help you to follow me through this process for mental clarity nonetheless. So let's start out this problem in what will turn out to be the wrong way. Because the denominator is a linear factor to a power, we would normally break that down into all linear factors leading up to that power. Since we have an x minus 2 quantity squared here, we'd have one factor with a denominator of x minus 2 and then one with x minus 2 squared. This is what we originally called the type 3 problems if you've watched that video. So at this point, if t and s are to exist, we would want to find them. And what we would do to find them is the same thing we always do, to condense these two fractions into a single fraction by the common denominator trick. To achieve a common denominator, I multiply by 1. You'll notice the blue thing is a 1. And now that I've achieved a common denominator by distributing the t, I can combine terms in my numerator over that common denominator and be done condensing this into a single fraction. Now, if you watched any of the other videos that I've produced on this topic, you're well aware that we now compare the results to the original problem. If t and s are to exist to make these expressions equivalent, then it would have to be true that their numerators were equal to each other, because after all, the denominators are both equal to each other as well, albeit in different formats, but equal nonetheless. So the question now is, how could the red polynomial ever equal the green polynomial? The red polynomial doesn't have an x cubed in it. So you can imagine, and look down at the bottom numerator in red as I say this, you can imagine that no matter what t is, no matter what s is, that numerator in red there will always be a linear polynomial in x. There's no way to get an x cubed out of an expression that doesn't have an x cubed. So we seem to have made some kind of an error here. And I'll tell you what that error is. The error was the assumption that I could break this down into the sum of two fractions in the first place. In other words, when I wrote the expression with the t and the s in it, I was sort of implicitly saying, assume that there are values of t and s for which these two expressions are equivalent. But what all this algebra showed is that there are no such values of t and s for which these values are equivalent. Now, when you're doing problems in partial fractions decomposition, there's a way to avoid these false assumptions. There's a way to sort of mitigate this circumstance of what if I make an assumption and it turns out to be false. Starting back over at the original problem, let's now take a look at what you would do, not what you wouldn't do. What makes this problem different than all the ones you've seen in the other videos is that the numerator has a higher degree than the denominator. If you've been watching all my videos, I've carefully orchestrated them for that to never happen up until now. You'll notice in this problem, the numerator has degree 3 and the denominator has degree 2. And therefore, since the numerator has a higher degree, we're not going to be able to split this fraction into a sum of fractions. Not until anyways that we've done something first. And that thing that we need to do, long division. I have a separate video on long division if you need to see it after watching this video. But here's the bottom line. When you have a numerator with a higher degree than a denominator, you first decompose it by the long division process. I'm going to take you through this long division problem in a somewhat quick fashion. If at the end of seeing this you need to go watch a long division video, that's fine too. So the way long division works is you always want to find something that will multiply by the first term on the outside to equal the first term on the inside. Once you find that, you multiply the entire outside by that newly created term, and then change the signs to mimic the subtraction that happens in long division. Once changing the signs, you combine like terms and start the whole process over again. Looking only at the first term of the outside and the bottom, ask yourself what times x squared equals 8x squared, and of course you come up with 8. 8 then multiplies by the entire outside expression or divisor, followed by a change of signs and a combining of like terms until the degree is lower than that of the divisor, which it is. At this point, you take these three quantities and you make a fraction, a sum of the quotient plus a remainder fraction, and that is essentially the quote answer to the long division process. But what we've really done here, I don't want to think of this as a problem and an answer. I want to think of this as the beginning of the decomposition. We've started by taking this fraction and decomposing it into the sum of two or three things here. So the decomposition has already begun. If you're very uncomfortable with long division, you can still watch the rest of this video and see how the process works, but you will have to supplement your understanding by going back and watching that, I'm assuming, as well. But even if you're not comfortable with long division yet, here's something to notice. In the top line, the numerator had a higher degree. Now that we've decomposed it into 2x plus 8 plus fraction, that fraction has a numerator with a lower degree and therefore can be decomposed. So what I'm going to do now is I'm going to keep the 2x plus 8. That's part of the decomposition we've already achieved, and I'm now going to decompose the fraction on the right. Treating the fraction on the right as its own problem and ignoring the 2x plus 8, which is already part of our answer, I can factor my denominator into x minus 2 times x minus 2, or x minus 2 squared. Then, because that is a linear factor to a power, which we would have called a type 3 problem if you've been watching my videos, I can decompose that into two fractions with unknown quantities t and s as my numerators. Notice I'm carrying the 2x plus 8 along each step, but I'm not going to use that in any of the calculations because I'm just trying to decompose the fraction on the right. So as usual, to decompose, we need to find out what t and s are. To find that out, we need to put those two fractions into one, so I will do the common denominator trick. Distribute the t, combine terms in the numerator over a single denominator. You'll notice once again that while 2x plus 8 is part of my answer, it's not part of my consideration at this moment as I decompose the fraction to its right. And now that I've gone this far, it becomes a matter of comparison once again, just like it always is. I've assumed that there are values t and s that will make all of these expressions equivalent. The only way that could be true is if the two x terms were equal to each other. But how could tx always be 24x? Well, clearly only if t were 24. And that's my first equation. But in order for all of these expressions to be equivalent, the constants have to match as well. In other words, negative 2t plus s has to have a result of negative 32. That makes my second equation and completes the system of equations I now have to solve to have decomposed this entire expression. This is a pretty easy system to solve. After all, we already know that t is 24. I could plug that into the second equation and solve for s. I didn't show the work here, but doing so resulted in s being 16. Let's not forget what all of this work shows. All of this work shows that if t is 24 and s is 16, that all the expressions on this page are equivalent to one another, and most notably, the two in black. So if t is 24 and s is 16, I can change those values and now have proved that the original problem is equivalent to the other black expression on this page, and that is my decomposition for this problem. Thank you so much for watching.